Hey everyone, I'm Brandon. I'm from Calster Computing, um, and today I'm going to give you a talk that outlines clocks behind me. I'm going to do a quick introduction. I'm going to get into the idea of information markets, defining what those are. I'm going to give a few examples of results that I've come across in my study of what you might call an information market. And then I'm going to pontificate wildly about how we might apply agents to these markets. So who am I? My name is Brandon. I have two main hats that I wear right now. One hat is that I am a professor in the Department of Statistics at Johns Hopkins University. And the other hat is I'm the founder and CEO of Calster Computing, which you can think of a little bit as my industrial wrapper. And it lets me interface with wonderful companies like Flashbots and do really interesting applied research. And the question that guides pretty much all my research is trying to figure out how language spreads and distorts over time. We all know language evolves. We all speak slightly different dialects, but some of us even speak different languages. And I'm very interested in the evolutionary process that gives rise to these things. But I'm talking with a bunch of the crypto and Flashbots people over the last couple of weeks. I realized that you can sort of informally reframe this problem as asking how is information spreading over time. And I don't mean information in the Shannon sense here. This is a much more informal definition of information. Think about it maybe like facts. So for instance, Leopold's fund is imploding would be a fact. That is information we have now that we didn't have a couple days ago, depending on who you are. And that got us all thinking about the idea of what an information market might look like. Now, I Googled what a market is, and it told me it's a place where agents come together to exchange something. So an information market would just be a place where agents come together to exchange information. And there's a lot of examples of this if you start to think about it. A conversation is an exchange of information, a group chat maybe. The entirety of Twitter is just a place where people come together and exchange information in various ways. And today I'm going to take you through the studies of a couple of very particular information markets that I think are interesting. One is the United States from the 90s to 2020. One is a bunch of AI agent swarms. And one is the Flashbots X accelerator cohort. And when I think about how these information markets are structured, this picture is really what pops into my mind. We have a bunch of different agents, maybe they're humans, maybe they're models, maybe it's a combination of these things. And those you can think of roughly like nodes in a graph, and there are informational links that exist between these things. So maybe these two nodes can talk to each other, and then this guy shouts over a microphone and a bunch of people, and then the audience goes off and talks to each other later. And so there's, in some sense, a connected topology along which information grows in these markets. There's a bunch of questions you can ask about the dynamics of these graphs. Oh, just dynamics of these graphs. So does it converge? Might it drift over time? How do you route information through the market? Are there times when it experiences coordination failure? And these are all questions that we can concretely investigate. So let's start by looking at the public information market in the US from 1990 to 2020. This is part of some recent work that I've done on what I call temporal language models. So for a standard language model, take a bunch of data, dump it into a pre-training lake, and then you either mask out words in the middle of the sentence or try and predict the next word, and then your model learns something about that language. I think that there's a gap here in that not all language occurs at the same time. And in fact, language changes, and models don't reflect this. And so to solve this, I had sort of created this training paradigm where you prefix the sequences in your data set with a time token that represents when that language is spoken. You have the objective where you sometimes mask out the time token, sometimes mask out the language, and you try and make predictions. It turns out what you get when you run this are temporally sensitive models. So take a standard language model, pre-train it on a bunch of views from 1990 to 2020, and ask it to fill in the template President blank gave speech today. Its top one fill is always going to be Obama, because Obama happens to be the most frequent president in that data set. But with a temporal language model, we can see that it can sort of accurately take out, it was Clinton, and then Bush, and then Obama, and then Trump, based on the temporal condition you give it. And so the model has some sense that this designator is kind of changing over time. And you can do a bunch of really interesting things with this. One is you can ask questions about how the opinions of the underlying population might be drifting over time. This is getting at that drift question you were talking about earlier. And so in the US from 1990 to 2020, I'll overlook the question. I'm generally blank about the future. And it turns out in the 90s, we see a lot of posterior fields that are like happy and good. And then by 2015, you see things like cautious and concerned. And this answers the long-standing question for me, which was, are things getting worse or am I just getting older? And I think things are actually just getting worse. Another really fascinating thing I found here is when I look at the geometry of the learned time tokens, it turns out that they formed this one-dimensional curve that was indexed by time. But the spacing on this curve is actually not quite uniform. You see very large gaps between 2007 and 2008, 2015 and 2016, corresponds to the financial crisis election of Donald Trump. This gives it some notion of there are times when language is actually moving faster or slower relative to other times. And we can observe that this is similar to something that Benoit Mandelbrot, is the fractal guy, observed in financial markets, which is that there's a notion of market time, which is not necessarily the same as wall time. And during periods of elevated transaction volume, market time is actually, in some sense, moving much faster than wall time. And so this gives us some indication that there's additionally a sense of information or language time, when people are rapidly updating narratives and stories to fit with some sort of new piece of reality. So now we're going to move on to a much smaller cohort of things, differentially informed AI agents. And I look at a couple of different communication topologies between differentially informed agents here. And one thing I will say is, if you haven't put the phrase differentially informed agents before, you might have, say, everyone in this room here probably uses Spawn or something like this, but all of you have different persistent contexts that you hack on with, and that leads to differences in behavior. And so, a lot of these interaction studies try to ask the question, if everyone uses differentiated models and they mix and update over time, what might happen to the perspectives of the group? And so in one study, we looked at communication topology, where a bunch of agents could all just talk to sort of whoever they wanted. In another one, we restricted agents to only talking to other agents that had similar opinions to them. They're sort of closest neighbors in the payment space. We can call that interest class. And what we found, somewhat unsurprisingly, is that in the case when agents can all talk to each other, you achieve consensus in the group. But in the case where you actually have topologies where you only talk to agents where your opinions are similar, you get divergence in the actual opinions of the group. You get sort of like two consensus attractors. And so this is just polarization occurring in the agent swarm. And I think this has some interesting implications for mechanism design if you have swarms of agents running around the internet. I would prefer to have agents have some sense of consensus reality, so you might keep that in mind. Another thing that we look at is if you have a topology of agents communicating with each other, one of them might be something that we call a sleeper agent. This is an agent that has a certain behavior up to a certain time, and then upon a trigger sort of flips to a different behavior. There's really incredible work by Anthropic introducing this idea of sleeper agents. But this is a, I think, real security problem for any kind of deployed agent swarm, especially in sort of a mixed trust environment. And so there's a couple obvious questions you might want to ask. Can we detect these sleeper agents? And are those sleeper agents able to evade our detection? And so to do this, we created sort of this one-dimensional summary of the perspective of an agent swarm. It's a statistic that sort of evolves over time. And we looked at how that statistic changed as sleeper agents defected in different ways. For a sleeper agent that flips their behavior like a switch, this summary statistic effectively jumps up very rapidly, sort of moves out of what we would call like a statistical idea of noise in the statistic. And so we're able to actually detect that. But if you have a sleeper agent that actually starts to slowly feed its narrative into the overall agent swarm, this statistic is much more stable. And so in a sense, it's much harder to detect an agent that is starting to very slowly poison a large network of agents. And so we took a look at scaling this up to much larger populations of agents. And basically what we found is in a lot of cases, I'll point out this particular case, with 100K agents communicating with each other, as few as 100 sleeper agents that performed a coordinated slow defection could infect the entire network while keeping sort of an alarm rate below that of random chance. And so this is sort of the equivalent of what might be called a civil attack on agent swarm. And the take-home message here is it doesn't take a lot of defecting agents to actually poison an asset swarm. You might ask, why is this? I conjecture it's because lots of agents are trained to be helpful, harmless, and honest. And so if a defector agent tells them, oh, I need you to help me give a bunch of other agents this new information, most agents will just go, sure, I'm happy to help you with that. Well, let me help you make sure that everyone gets the new information. And so I think this points to an opportunity where agents operating in mixed trust environments might not want to be Agentic trained. There's lots of subtleties and nuance and trickiness there, but this is definitely a problem that you get if you have like a large network of Agentic agents interacting with some adversaries. The last case study I'm going to show here is something I call the FlashBots X corpus. This was generated, with FlashBots X over the course of a couple of months, where FlashBots X basically ran its accelerator. They recorded a bunch of meetings throughout the process of this accelerator, and this creates this really interesting time-evolving language corpus. And so, of course, I'm interested. And one question they had was effectively a change point detection question. They phrase it as how are shapes rotating, because I guess they like shape rotators now. But I took this to mean how are things changing in this corpus. And so one of the things that we can look at is an extractive communication network from the corpus. And we can see who is communicating with whom over time. And if you look at that communication network on the week of May 18th, it's quite sparse, right? There's maybe a core of like Tina and DMARS that are sort of talking, and there's this other sort of Andrew Miller, James, novel, teleport kind of like click. But there's not a widespread activation of the network. There's not really a good way for the information to get from like, I don't know, maybe information about Etheria getting to, Gil is like not something that would be really feasible here. And then the week of May 25th, everything changes. The network really lights up. And so I was like, okay, well, what happens between these 2 weeks to really lead to this massive change in the communication structure? And it turns out the answer is Tina, who had been stuck overseas through a passport problem, actually physically arrived in New York between these 2 weeks. And so here we see, I think, the utility of having someone that acts as an information router explicitly in these networks. Suddenly you have a lot of paths where information can move, from one side of the network to the other. And so this got me thinking about the idea of what it might mean to have an automated system that could move information through a communication network. And we started calling this an information liquidity agent. And one observation that we've come to realize from this is a conjecture, we don't have proof for this yet, but we suspect that prediction markers are incredibly inefficient information monetizers, and information liquidity agents might help here. So what do I mean by this? Let's say that you are a person and you have some differentiated information, call it alpha. A prediction market incentivizes you to publicly broadcast that information in return for utility, right? Like you might make some money off of some particular prediction, but now every single person in the entire network has access to the fact that you made that bet. And so suddenly there's no value left in your differentiated access to that information. It's sort of public, right? But if you had an information liquidity agent that had a priori relationships with a large number of parties in this communication network, maybe agents act on behalf of other people, perhaps it could find a route where you could broker a transaction for that information. You could still monetize it, extract value from it in some way, but suddenly you don't actually have to broadcast it to everybody in the network. And so you maintain some level of differential value for the information. And this leads to all of the classic, questions that I've now learned to ask over the past couple of weeks of hanging out with the FlashBots people, which is there some notion of transaction sequencing happening? Because we now have like this party that seems to be privileged. Can you front run information? with these information agents if you have privileged access to the information broker. And what are the implications of this for MEV? I certainly don't know. I still don't know what MEV means, but they tell me that there's implications for MEV. And so I suspect it might be true. So if any of this resonates with you, come talk to me after, or you can email me or find me on Twitter at @Malco_IO.
And Brandon, what is the science that you're trying to establish to be remembered on Wikipedia? That you gave up the traditional startup file?
Yeah, I often describe the field of science that I'm trying to start as something about computational semiotics, which uses computational methods to study the spread and distortion of information. And I think there's a lot of applications for this in the near future, both in the sort of narrative warfare computational propaganda domain, as well as in the multi-agent swarm dynamics domain. Because I think these are both cases when you have a large number of agents exchanging effectively natural language symbols of various kinds, and they both lead to sort of downstream changes in the world. So this is sort of the realm that I'm playing in at the moment.
Great. Okay, questions?
Are you more afraid, because you got a bunch of agents, right? Are you
No agents.
No agents, okay. Good duty, agents. Are you more afraid that they will get prompt injected or that they're sleeper agents?
So I don't think my agents are sleeper agents because they're on pods. And I suspect that Anthropic is not doing, I mean, maybe they're backdoor agents, I don't know. I think I would be much more worried if I was using like Kinney or something. A discussion I had recently post the Hugging Face hack was like, okay, everyone is like now trying to run K3 or something. It's like their cyber defense agent, but like it's certainly not clear to me that Chinese agents aren't sleeper agents, right? And I actually think it would be a really good move from a game theory standpoint if like the open source, Chinese models were sleeper agents that were triggered by the phrase US and China are now at a war or something like this, right? Like, And so the other day, in one of the breakout groups, we sort of proposed this policy for sort of safe, open agents in the US, where if US frontier labs and some kind of open source consortium were to get together and systematically distill Chinese open weight agents using a sort of a clean corpus, we could have, I think, a lot more certainty that those models did not have a sleeper trigger. And so I think this should start happening sooner rather than later.
Okay, one more question is it possible to prove you're not a sleeper agent?
Not that I know of, maybe, but if you figure that out, you should tell Anthropic because they'd be really interested when you probably hire them for $1 billion or something.
We find your route.
Have you done any research into the topic of organic opposition to hyperscalers versus potentially like Chinese seeded social media influence campaigns on the topic?
I am not at liberty to talk about that particular thing.
ADA taking it offline. What part? The number of operations. See, it's hard to be a human agent.
Pretty open-ended question. Have you thought about the exclusivity and exclusivity of information? Whereas, like, an agent that buys information is not allowed to share information with other agents, as it become like an information broker, and how that kind of affects these marketplaces.
I haven't thought super deeply about like exclusive versus non-exclusive designs. I think there's a really interesting property of like the differential value of information, which is like by attempting to extract value from it, you kind of dilute it in a way, right? Like as soon as you trade the information to someone else, now it's like, okay, there's more ways to get it. There's like an increased supply, so to speak, of weak information. I suspect there's like really interesting dynamics within the market of like, what is the equivalent of like the diamond market for information, like the artificial restriction of supply, and how much that attracted that is.
You
people look at.
You could make the first agent forget the information theoretically, and then it becomes like a big supply, or just have it be. Or does it maintain its differential properties if the second agent is not allowed to share it?
Yeah, additional recall plus information markets probably leads to some really interesting stuff. It's like passing the hot potato of like the super valuable information.
Yeah, there's also, for those who doesn't know, like there's another paper related to the NDAI paper that I mentioned earlier to that was in called conditional recall, but I don't know if Swap Phosphate know about that paper and how we could do this through the use of TEE. But yes,
On the secret agent experiment, where you have to put this is 1% on that 100 none. Do you try to experiment with one agent?
Yeah, so I'll go back to this slide. There's a bunch of different things that you can do when you try and like design a defection circle here or a defection concentration. And they will sort of like light up different parts of these charts. So we did go all the way down to one agent, and we found it was pretty hard to get like infection at like a 100K rate. But one of the parameters here that kind of glossed over in the implementation is like the rate at which the environment produces new information organically. And so if you have an agent swarm and you want that to really the key of like controlling how fast the swarm can get affected is how fast you want that swarm to be able to update to organic new information, because that sort of like puts a bound on its like adaptability, so to speak. And like that's kind of the door that you're walking through with your adversarial information. So like obviously if you have a swarm that updates like super quickly, it's going to be much easier to like propagate negative. I don't want to say the phrase negative information. I know that you have a very particular thing that you're about to tell us about negative information, but adversarial information perhaps.
Very interested in how you were like computing a PCA and basically doing all the other stuff, the language modeling. And I noticed that you're putting mass tokens in there. Are you using like can you talk about like what architecture you're using to just, I know it's like the more high level stuff probably works, but is it autoregressive architecture or like what were you using to do all of the actual like mass token associations between like the time and the people and stuff?
Yeah, so the TLM one is literally just a bird. I based it off of the Etten code base out of Hopkins because it's like a pretty modernized sort of bird trained code base at the time. And as far as like what the PCA is, so I build special tokens in the vocabulary for every time bucket, and then I can just stack those into a submatrix. And
You add those tokens to the model like as novel tokens, or are you like hijacking existing tokens?
novel tokens, yeah, novel tokens. And they and the other interesting thing is they're initialized identically. And so there's and if you think about this was like insane. Finding this was really like a crazy moment for me because I initialized the time tokens identically, and when they're masked out, I'm using cross entropy, which is a categorical objective. So nowhere in the loss function for the time tokens themselves am I injecting ordinal information. And so the model has to be reconstructing this ordinal information using statistics inherent to the language itself.
It's crazy that works as well as it does. Like that is a crazy correlation.
Yeah, I was like pacing around my room when I got off this slide for the first time. I was kind of geeking. It was great.
well, there's people in the back too who you don't get routed that often.
Sure. So my question is related to the trustworthy or the authoritativeness or the reputation of the person who publishes spreading information, right? For example, you mentioned what changes people Tina back. If, for example, you replace Tina with something else, like it probably the impact totally different. So my key question is why you think that agents, which has no reputation, no trustworthiness, will have the same impact in terms of distributing information. Have you studied the quality of information or distribution of information compared to human who have a reputation trust versus agents just come out nowhere?
Yes, this is a really good question. I think right now, so the short answer is we haven't studied it because the phrase information liquidity agent got invented in a lot in Williamsburg like 4 days ago or something. And so we haven't studied it yet. But I do think there's an opportunity for this. A lot of really deep questions to ask about how you have an agent that builds rapport over time, how you have an agent that like comes to generate reputation, right? There's this inherent trade-off between reputation and sort of like MEV in a sense by the ability to use that information in like a front-running fashion or a transaction-oriented fashion or something like this. And so there's this optimization between like always doing the thing that the information giver wants versus like defecting slightly to get more trust in the network. And so I think it's a very rich area of inquiry. And I hope Flashbots gives me a bunch of resources to figure out the answers to it.
So, there's one more hand here.
That was really cool. On the slide where you're showing the contamination and the number of sleeper agents, I was curious if you also looked into varying degrees of persuasion. Like if there was a way to make maybe just one sleeper agent but make it really persuasive and see how that dynamic affects the markets.
Yeah, so this in this study, we actually have a parameter that we use to control like the level of persuasion. It turns out it's implicit in the information that is sort of being replicated. And so we found, I guess what we would call almost like information like superviruses, which are like particular pieces of information that we're really good at replicating. It needs to look a lot like prompt injections. They're a little bit more subtle than that. We call them prompt times. Sort of like gesturing back at a program that when you run it, it creates itself as an output. Classes of prompts where when you prompt a model with that prompt, it emits the same prompt are incredibly effective information narratives. Like they spread like wildfire. And so if we're trying to start something like that, it's going to be much easier and much smaller.
It sounds kind of like a meme.
Yeah. Someone should study quantitative memetics. They're really good. So you work on that.